page 2 of the I/O notes. So let's just look at the I/O device interface a little bit. I've just given you some names of some I/O devices and these weird, pretty arbitrary address ranges. And the way an I/O device works is it's got a connection to the outside world, and then the controller or the interface has connections to the bus, which connects it to the processor and memory and so on. So for example, Ethernet, there's 8 pins on a normal Ethernet connector. You plug a cable in there on the side of your computer if it has such a plug, and there's some hardware there that knows what to do with those signals. So there's like an interface that knows how to drive those lines or to sense them, and then it's got some logic for interpreting what's going on. Another example, an older example, is the serial bus, which uses the DB9 connector. There's 9 pins. It actually used to be 25 pins, but they shrunk it down to 9. There's 1 pin for transmit, another pin for receive, and then there are a couple more pins. Let me just show you that. So this is a DB9 connector. So 5 pins across the top, 4 across the bottom, and they're numbered 1 to 9. I don't remember which is receive, which is transmit, and so on. Let's just say that that's the receive pin, that's the transmit pin, and then there's some control signal pins as well, like ready to send, clear to send, stuff like that. So anyway, so you got this physical connection, you've got some circuitry that knows how to interact with those wires essentially, and then the side that connects to the computer. So if this is our I/O device, it's got an external connection, such as that, that 9-pin connector that I have drawn above there. And then on the other side, it needs to be able to talk to the rest of the computer, so it's got connections to the system bus. And so there are going to be a number of registers that are part of the computer-facing interface for this I/O device. And they have a number of, flavors. So you're going to have at least 1 control register, so you can write values to that from the system bus, and that will control its behavior, whether it allows incoming data to come in or stuff like that, or whether it allows it to interrupt the processor. Then there's a status register. There's usually at least 1 of those that you can read that will tell you information about the state of the I/O device. And there's usually at least 1 data data register, or sometimes it's called a buffer. And that is, if you're sending data, then from the CPU, or the processor I should say, you're going to write stuff to the data register on the I/O device interface, and then that will, the circuitry over here will send that out the external connection, or data that's coming in will be received and put into a data buffer that can then be read from the processor. So let's make this specific. I'm choosing the UART because it's a relatively simple I/O device, unlike, say, a USB host or an Ethernet controller or something like that. So UART starts for universal, universal asynchronous receiver transmitter. So that's where the name comes from. it is the serial port, called serial because you can only send or receive one bit at a time. It's not a parallel communication. Now it puts those into frames of 8 bits or bytes that get sent one after the other. Okay, so it used to be purely asynchronous, and the receiving and sending of data was controlled by these control signals, so both sides would drive them in this kind of handshake to indicate, you know, when the data was ready to be read, when it had been read, stuff like that. But then they added a clock to it, which is going to be faster, so it became the universal synchronous asynchronous receiver transmitter, so USART, but nobody calls it that, they just call it a UART, but technically they're USARTs now. And some example registers on the UART 0 on the LPC 1768 are the data register. One of them is called the receive buffer register, or the RBR, and we're going to be looking at this, and that is mapped to address 4000C000. So if we read from that memory address, we're going to get 1 byte that came in from that external connection, and we'll read it into a register in the processor. An example of a control register on this particular I/O device is the interrupt enable register, or the IER, and that is at address 4000C014. And why that address? Why is there that jump there? It would just have to do with the design of the hardware for the UART, and for whatever reason, the decoding of the addresses, it made sense that that register had that address. And, oh, I'm sorry, I made a mistake. That's C004, so there isn't a jump, assuming, well, there is a jump because the RBR is only 1 byte in size. Okay, and then an example of a status register on this UART is called the line status register, or you guessed it, the LSR, and that is at the address that I just tried to write above, so 4000C014. Okay, this UART, in its interface, there's somewhere in the neighborhood of 20-30 registers, so even though it's a simple I/O device, the interface is still complicated enough. We're just going to focus on, you know, a little bit of it. So let's just do something here. So let's enable interrupts. So an interrupt is an asynchronous signal from the I/O device to the processor that says that it needs something done for it. It needs service. And so let's enable interrupts when data is received. So I'm going to show you the code and then I'll elaborate. So here's the line of code that would do that. So LPC underscore UART arrow operator IER. So LPC underscore UART is a pointer to a struct that defines all the registers in the interface for the UART. And next I'm going to use the pipe symbol, and that's the logical OR, so that's a bit by bit OR of the 2 operands. And we're going to do a bitwise OR with the IER RBR, and this is a constant that's defined in a header file, and so it's going to toggle a bit in that control register. It's going to, I shouldn't say toggle, it's going to turn it on So it'll read out all the control register's contents, it'll set that 1 bit, and then it will write it back to that control register. And now we've enabled the UART to interrupt the processor whenever it receives data. Looks like magic. There's not a lot of, well, it looks like gibberish, really. So let's just give you a few more details here so you can start to understand what's going on. So this, the next 3 lines are from uart.h, which is one of the files that you include when you do your your projects for the labs. So in that file, if you open it up and look, there is a line which is pound defined. So it's when you see the pound, it's a preprocessor directive, and it's saying define this macro IER underscore RBR, and then it uses a hexadecimal program literal 0x01, and now it's still an integer literal, so it's actually going to be 32 bits, but we're going to be writing it to an 8-bit register. So I'm just going to show you what that equals as an 8-bit binary number. So subscript 2 means that that's a binary number there. So it'll get truncated down to 8 bits when it gets written to that memory address. Okay, next line. We're going to define 3 macros. So pound define interrupt enable register, transmit holding register enable, THRE. So this is when you want to send data out, and you want to know if, is transmit holding register empty. So if you want to be interrupted by the I/O device when it's ready to send more data, you would set that bit in the interrupt enable register. And as a binary number, this is what it looks like. There's 2. So they're different bits. So we're setting different bits in that register, and we're controlling the behavior of the UART. And one more, the interrupt enable register receiver line status. So if there's something up with the status of what we're receiving, then we want it, and we set this bit in the interrupt enable register, then the processor will get interrupted when there's something going on there. So these are bitmask. Whoops, bitmask. So they give names. So bitmask give names to bits in the register in this particular application anyway. Okay, so actually I want to keep my green here. Not going to change color. So now from uart.c, which you also include in your projects, there are some lines of code, and I've shown you one already. I'm going to leave a little bit of space to the left so I can add some text there, and a little bit of space above. So this line we've seen already. I'm going to write it again. I've got a reason for that. Whoops. Don't have a reason for not using the arrow operator there. Okay. So that's the first line. I'm going to show you 3 lines, but let's just over here model the contents of the interrupt enable register. So on reset, you can look this up in the LPC 1768 user's manual. The bits in that register default to 0. That's typically the case, and it's default behavior. So when we when we do a bitwise OR, this value here is 0, 0, 0, 0, 0, 0, 0, 1, and we are doing an OR here. So I'm trying to remember the predicate logic OR. I'll just do the plus sign for a logical OR. So we're going to do a logical OR those two bits, so we get a 1, do a logical OR those two bits, we get a 0, etc. Right? So that's a bitwise OR of the bit mask plus the contents of the register, and so this resulting value gets written back to the register. Next line, LPC UART arrow operator IER interrupt enable register OR equals IER RLS. And so let's go back to green here. So what we're going to OR the contents of this value here with that bit mask, and the value of that bit mask, if you look above, was this. So we OR that together. So now we've got 1 or 0, true or false is true, 0 or 0, 0, 0 or 1, 1, 0, 0, 0, and the rest is zeros. So that's now the value in this register. So here what we've done are we set bits in the register, and now let's do an example of clearing a bit. So same register. If we want to clear a bit, we do a logical AND with not the value, not the, well, okay, let me write this out first, IER, RBR. So if we want to clear that particular bit, we want to set this bit here to a 0. If we do AND equals with that, we're actually just going to get all zeros with a 1 at the end, which is not what we want to do. We want to set that bit to 0. So what we have to do is use the bitwise NOT operator. So the complement of, or the bitwise NOT of the IER RBR bit mask is going to be 1, 1, 1, 1, 1, 1, 1, 0. Up above, if we look right at the top here, that's what it was that 0, 0, 0, 0, 0, 0, 1, complement it, and then we're going to AND it. And so I'll use the asterisk for the AND operation. So 1 and 0 is 0. 0 and 1, 0, 1 and 1 is 1, 0 and 1 is 0. So we're doing each of these bit by bit, right? And so down below, we got a bunch of 1s. So basically whatever is above the 1, that's what comes. So 1 and anything gives you back that value. So we just managed to clear the first bit. So that bit's now a 0, but we left the rest of the register alone. So this is a bitwise OR. This is a bitwise AND, and this is a bitwise NOT. And when you see that with the equal sign there, what it's doing is it's going to do it. Writing it with the equal sign saves you writing out the left-hand operator twice. So the thing to the left here, this part here gets ANDed with this part over here, and then the result goes back into this part back over here. And so this is an example of clearing a bit.